Clouds play a crucial role in our day-to-day weather and our global climate. This is seen most clearly by observing the water cycle in the atmosphere. The water cycle is the cycle of moving and transforming water molecules from liquid form to vapor form and back again to liquid. We begin with evaporation from oceans and other bodies of water. As this air rises, it condenses to form clouds. The wind in our atmosphere moves these clouds over land, leading to precipitation. And as rain and snow accumulate on the ground, they produce water for lakes while producing runoff back to the ocean, completing our total cycle. This means that the development of clouds, the growth of clouds, and their movement around the globe directly affects all of the weather that we sense and the climate that we experience on a year-to-year basis. In this video, we will investigate the basic ingredients that are needed to form clouds, and then we will use that information to understand how thick storm-producing clouds are formed. In this video, I'm going to demonstrate how you may produce a cloud in a bottle. And we're going to examine this problem using the standard details you would receive from the scientific method. So that means we're going to first think about the major variables that we think should influence the development of clouds. And then what we're going to do is that we're going to test each of those hypotheses using a simple cloud apparatus. We're going to use a bottle of water and a plastic bottle. And what we're going to show is that based upon the variables that we choose, we will see situations in which a cloud does form and situations that clouds do not form. Now, if you were to ask most people in terms of their understanding of the science of cloud development, they would say that the most essential ingredients for a cloud to develop is the presence of water vapor in the air, and that should be enough to form clouds and everything else. Now, here's a quick test of whether or not that is true. We now have a bottle of water where we have liquid water in here, and we have tied the top tight. So that means if we shake this around a little bit, that means we are placing lots of water vapor molecules on top of the actual liquid water surface. So that means if water is the only essential ingredient that is required for a cloud to form, I should be able to see that right now. And notice there is no evidence. There's no evidence of any sort of condensation happening in the bottle. Now, the question you may ask would be, what if we decide to increase the temperature of the water? So now we're going to change the temperature of the water. So I now have a second bottle, and this bottle is substantially warmer than the other. The first bottle, I measured the temperature and it was about 50 degrees Fahrenheit, so relatively cool. This is at least 80 degrees Fahrenheit. And now, same exact experiment. If you look here, changing the temperature of the water isn't changing the development of a cloud inside the bottle. So something else must be missing in this equation. The next question you may ask is, what if we decide to change the pressure? Because we expect that in the atmosphere, as we go high above the surface, the pressure of the air gets less and less as we go up, and therefore clouds should form in an environment in which you have lower pressure. Well, for a cloud to exist in the bottle, we can change the pressure just by squeezing and releasing. And what you see here is that regardless of how hard I squeeze, you still do not get any condensation occurring in the process. So that means temperature by itself cannot produce a cloud. Pressure changes by itself cannot produce a cloud, nor can water in the presence of water vapor inside the bottle produce a cloud. So the next question we have to ask is, what is missing inside of our bottle here that exists actually in the atmosphere? And this is something that requires just your observations. If you've ever been in any major city in which you have many sort of industrial factories and things of that nature, you have plumes of smoke going into the atmosphere. And what you will notice is that as those plumes of smoke rise, you begin to see clouds and other things form. So the difference between the environment inside of this bottle versus the environment outside is probably going to be the presence of all of the things that are in the air. So one way to reproduce or to recreate the environment that is outside and compare it to what's in the bottle is to try to get smoke within the bottle. And the simplest way to do this is to use an actual lighter or to use a match and put it on fire. So in our case, let's take some matches that you see here, and we're going to take a match, we're going to strike it, and we're going to put the smoke inside of the bottle. So let's open our water bottle here, and now we're going to strike a match. And now we put it inside, and now we close the lid. And we now swirl it back around. And now we're going to ask the question, is this adding the smoke inside of the bottle enough to make a cloud? Well, if you look at this, you already see there's smokiness inside the bottle. Now let's see what happens when you change the pressure in the bottle. So if I squeeze in, nothing appears, but when I squeeze out, notice you get condensation happening. So once again, squeeze in, and notice that the cloud disappears, and then squeeze out, and notice you get condensation occurring right here on top of the water. So that tells us that the missing ingredient in terms of making a cloud is the actual particles in the air that come from the smoke. So that means if I squeeze again and let it go, notice you get a cloud that is absent, cloud forms. Cloud disappears, and cloud forms. So if you put that together, that means you have the essential ingredients needed for cloud formation. You certainly do need water vapor in the bottle. You need to have some way to change the pressure and the temperature. But without the actual particles of smoke inside here, you will not produce a cloud within the bottle. And that is the main feature that you should see here. So now what we're going to discuss is, why is it that smoke particles, such as striking a match, allows you to have a cloud disappear and a cloud to form? Why do smoke particles actually aid in cloud formation? Now, as we have seen, the condensation process that produces clouds is not just as simple as having a large amount of water vapor that is present. There's an important analogy needed to understand why the presence of smoke particles can help form clouds. Just as dew and frost need a surface to form on, such as grass, there must be airborne particles on which water vapor can condense to produce cloud droplets. Now, although the air may look clean around you, it never truly is. On an ordinary day, a volume of air about the size of your index finger contains between 1,000 and 150,000 small particles. Since many of these serve as surfaces on which water vapor can condense, they are called condensation nuclei. And as we have seen with our experiments, without condensation nuclei present, it is almost impossible to see cloud formation. Now, when it comes to condensation nuclei, there are two types that are relevant. Some particles are known as hygroscopic, which means water-seeking, and water vapor condenses upon these surfaces very easily. An example of this in terms of our experiment were smoke particles. Smoke particles naturally attract water vapor to itself, and they are allowed to actually have condensation to happen. Another example of a good hygroscopic nuclei would be salt. Ocean salt, for example, is very hygroscopic, and this is one of the reasons why cloud formation occurs vigorously over open oceans. The other type of particle that exists in the atmosphere are known as hydrophobic nuclei. And as the word says, these are water repelling. Examples of hydrophobic molecules would be things like oil or gasoline. Hydrophobic molecules resist condensation from occurring, and that's because they resist nuclei from attaching to it. Now, it turns out that most of the molecules that we have in the atmosphere, most of the particles that exist, are going to be closer to hygroscopic rather than hydrophobic. But there is a distinct difference between the two. Now, in order to understand why the actual hygroscopic nuclei are needed in order for condensation to occur, we have to discuss the concepts of temperature and relative humidity. To understand how gas molecules can condense on condensation nuclei, we must explain what temperature is. For a gas, temperature is a measure of the average speed or motion of the air molecules that is in the air. As you see in the animation, as the temperature decreases, the speed of the molecules decrease as well. And as the temperatures increase, the speed of the molecules increase along with it. The same is true for water vapor molecules in the atmosphere. The temperature within the air is going to determine the average speed at which the molecules travel. Now, this concept is connected to the concept of relative humidity. Now, to understand how the whole process happens, let's think about what happens as the temperature decreases versus increases. As you see in the animation, when you lower the temperature within your system, that means the molecules are not moving as fast as before. That makes it easier for them to come into direct contact with the corresponding condensation nuclei. Now, when the temperature is high, water vapors move very quickly, making it difficult for them to directly contact the cloud condensation nuclei. So the idea here is that in our experiments with the bottle, when we have relatively low temperatures, the water molecules are not moving as fast, and therefore they can cling to the molecules, cling to the condensation nuclei. Therefore, if you want to actually see a cloud form, we need to have relatively low temperatures so that the water molecules are moving somewhat slowly. We also need to have a hygroscopic nuclei so that water molecules can easily attach onto that particular surface. And finally, what we need to have is this process to occur long enough so that condensation can occur and that you can see the cloud in the bottle begin to happen. Now, the next point that becomes relevant is when we have the cloud in the bottle, what we saw was that we saw very thin clouds within the actual bottle. But the question remains, how do we actually obtain clouds that produce rain? So how do we get the thick thunderstorm clouds that you see here, either from a supercell thunderstorm or from, in our case, a monsoon? Now we're going to discuss two mechanisms which produces this. And these mechanisms will come together quite nicely in what we call the Bergeron process. Let's think about small cloud droplets that exist in the atmosphere. Now that cloud droplets have formed, we will try to understand how they can grow to the size of a rain droplet or to a raindrop. One such way is through what we call collision and coalescence. Cloud droplets will be carried by air currents within the cloud. And if they bump into each other, that would be called a collision. Now, if they collide, then they will stick together sometimes. And if they stick together, this is what we call coalescence. So in terms of the picture, as small droplets collide and coalesce, they grow in size to becoming large cloud droplets. And as they get larger, they grow in size, and that means it becomes easier for them to fall based upon their weight. Now, although this process is important, especially within the tropics, and in terms of increasing the size of pre-existing raindrops, this is not the primary mechanism by which we get raindrop sizes. The actual process is named the Bergeron process, named after the scientists who discovered it. The Bergeron process can be summarized as follows. Within the cloud, the air reaches saturation, and some of the droplets come into contact with ice crystals that we call freezing nuclei. So that means we now in the cloud have a combination of ice crystals and cloud water droplets. Now, from the perspective of the cloud droplets, the air is at saturation. However, from the perspective of the ice particles that are coming down, the air is what we call supersaturated. And supersaturated means that the relative humidity is greater than 100%. Now, what happens is since ice crystals are supersaturated, they will grow larger at the expense of the water droplets. And therefore, as the crystals fall, they will go through now the collision and coalescence process, where additional cloud droplets will begin to form on top of the ice crystals, and they will collide, they will grow, and that gives you the rain size sort of particles we expect in clouds. Now this provides an overview of how clouds form from small cloud droplets that you can see within a cloud in a bottle experiment to the size in which they become supercell storms that produce heavy rain and precipitation. Now, for the interested student, there are many ways to change the design of this experiment in order to produce different effects. So here are some different experiments that you can try. The first would be to change the condensation nuclei in the experiment. What this would mean in this case is that instead of using smoke particles, you can try other hygroscopic nuclei, such as you mentioned before, salt, but think about any other particle that we tend to see in the atmosphere. Think of dust, think of dirt. All of those can be considered different types of condensation nuclei. And then you can repeat this experiment and to see whether or not the cloud that you get in your bottle is thicker or thinner based upon what is present. The second would be to change the water temperature. Now, as I demonstrated, I started with temperature of water that was around 50 degrees Fahrenheit and increased it to about 80. But think about what would happen if you have water that is near freezing, or think about what would happen when you have water that is above, say, 90 degrees Fahrenheit. You can investigate how easy it will be to form clouds when you have much greater extremes in temperature. And finally, you can change the pressure within the bottle. Now, in my cloud in a bottle experiment, I changed the pressure by squeezing the bottle and releasing the bottle. That gives you one way to change the pressure. But there are many different ways in which you can increase the pressure within any plastic bottle. For example, for those of you who have bikes and you have bike pumps, you can attach a bike pump into your bottle and pump air directly into the bottle. That's going to substantially increase the pressure, and that means you're going to have very different effects when it comes to cloud formation.